Hello everyone, now we are going to discuss the next topic, that is vibration on running mechanical system, also known as force damped system. My dear students, we have seen in the natural vibrations that in the natural vibrations we don't consider kinetic frictions and the unbalanced force. But as we study about the damped system, we have considered kinetic frictions. But in case of force damped system, we will consider kinetic frictions as well as unbalanced forces. So basically, this is the vibrations on the running mechanical system. So in this mechanical system, I'm going to consider a spring, and there is a damped system that is represented by the symbol, and there is a mass and is going to be attached with this system. Okay, so this is basically a running mechanical system. So at t barabar, after some time, the position of the mass will be this. Okay, and the force would be, unbalanced force would be, we have know that F naught sine omega t. Sine omega t. This is the unbalanced force. So where we know that F naught is maximum value. F naught is maximum value. And what is the maximum value? In the rotating unbalance, it would be m e omega square, whereas in case of reciprocating unbalance, there will be a m reciprocating r omega square. Okay, mass of reciprocating, or you can say mass of the system or mass of the machine element. Now, omega is what? Here, omega representing the speed or force frequency. This is the force frequency or speed. Now we are going to apply the D'Alembert principle. As you know very well, how can we apply D'Alembert principle? This is the body having a mass m. Now it is going to be in a motion in the downward directions, and the unbalanced force is F naught sine omega t. This is a running mechanical system. So there will be F naught sine omega t, but in the opposite directions of motion, there will be a spring force, that is X, and there will be a damping force, that is Cx dot, and of course there will be inertia forces, there will be Mx double dot. So now you just have to apply the D'Alembert principle and write down the equations. So I'm going to write down the equations like that. It would be X double dot plus C by M X dot plus S upon M X is equal to what? Is equal to F naught upon M sine omega t. Sine omega t. Now we just have to rearrange these equations. We all know that C by M value is what? Here I am going to write the C by M value. C by M is equal to 2 zeta omega n, where zeta representing the damping factor or the damping ratio, omega n representing the natural frequency of vibrations, where C is what? C is the coefficient of dampiness. Okay, so there will be a x double dot plus 2 zeta omega n upon. You cannot write it as c by m because sometimes in the examinations they will give you the damping ratio, damping factor, and they will give you the frequency of natural vibrations. So you can say natural frequency. We just have to convert it into this form. So this would become c by m is equal to 2 zeta omega x dot. You can consider it in bracket plus what is s by m? We know that s by m is equal to omega n square. Omega n square x is equal to f naught upon m sine omega t. This is the important equations. This is an important equations of force damped system. You have to note it in. This is the equations of force damped system. Very important equations. What is the difference between the damped system equations and the force damped system equations? The difference is that there will be a f naught upon m sine omega t is considered because it is a running mechanical system. Okay, but damped system is not a running mechanical system. This is the vibrations on the non-running mechanical system. So that's why there we are not considering f naught upon m sine omega t. But in case of force damped system, we have to consider the f naught upon m sine omega t. Okay, this is the equation of force damped system. This is the this is this is the equations of this is the equation of force. This is the equation of force damped system. Force damped system. So what would be the solution of that equations? You have to write down the solution. This is the equations and the solution would be according to the differential equations process. So the solution is we know that solution is basically x is equal to cf complementary function plus particular integral. Okay, the solution is a combination of complementary functions and the particular integral. So we have to calculate the particular integral and complementary functions as well. When I'm talking about the complementary functions, you need to understand that CF, first we are going to calculate the complementary functions. CF. See, there are three possibilities for the damping factor. First, zeta is equal to 1 and zeta is less than 1 and zeta is greater than 1. We all know the damping factor and damping factor having three values. It may be less than 1, it may be equal to 1 and it may be greater than 1. Okay, but we know that in case of equal to and greater than there is no vibrations because when the damping factor is greater than 1, this is the condition of over damped system, whereas when the zeta is equal to 1, this is the condition of critical damping system. So in both the cases, we don't get any vibrations because the vibrations basic definitions is to and fro periodic motions. To and fro periodic motions about the mean equilibrium position. But when we get the equations in the overdamped system, we find out that this is the exponential equation. So in that, when you draw the exponential graph, so there will not be any periodic motions you can get. But in case of underdamped system, we can get the to and fro periodic motions. So that's why this would be considered as vibrations. So there will be a vibrations. So only one possibility where the vibrations will be there. So after some time, when I consider after some time means very less time. After some time, after very less time. This is a very less time. Important thing. means you can say tends to 0. CF tends to 0. CF tends to 0. Why I'm going to say this? You need to understand. You need to understand the equations of the CF, that we have seen there is an amplitude which is an exponential decreasing functions. Are you getting my point? When we get the relations in the underdamped system, CF would be complementary functions comes out to be decreasing exponential functions. So decreasing exponential functions in the sense that when in a very less time, that complementary functions becomes 0. Okay, as time goes on. So that's why it becomes 0 after some time. But the thing is, x is equal to, if the complementary functions become 0, that means that solutions becomes 0 plus PA. That means solutions becomes equal to PA. Solution is equal to PA. Now we have to calculate the value of PI, particular integral. So I am just calculating here the particular integral and showing you how to calculate. See, PI would be calculated as f naught upon m. This is a process you have seen in the differential equations in the mathematics subjects. This is a mathematics process. F naught upon n sin omega t upon d square. D square is the differential of second order. 2 zeta omega n b plus omega n square. Okay. So when you solve these equations, you will get the final result. I'm just writing here the final result because this is the same procedure you study in the mathematics subjects, and the procedure is not important for you, but the result is very important. So I'm just writing here the result, that f naught pi is equal to, this is particular integral, is equal to f naught upon s under root of 1 minus under root of 1 minus omega by omega n to the whole square plus 2 zeta omega by omega n, 2 zeta omega by omega n whole square. Okay, multiply sine omega t minus pi. This is the solutions of the force damped equations. Again, I am explaining each and every terms. The result is part x is equal to particular integral we have seen. Okay, so particular integral comes out to be, in case I am talking about the force damped system. This is the case of force damped system in which particular integral comes out to be f naught upon s upon under root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square sin omega t minus pi, where omega representing the force frequency or the speed of the system. This is the vibrations with the frequency omega. Omega is this is the vibration with frequency. Vibration with frequency. Vibration with frequency. This is the force frequency basically. Force frequency, or you can see this is the speed. This is speed. Okay, and representing as omega. This is. So after some times, we have seen that after some times complementary functions becomes 0 because it is the exponential decreasing functions. So after some times CF tends to 0, but PI will not be 0 because there is no exponential decreasing function of time. So it will remain always in the running mechanical system. In the vibration of the running mechanical system, there will not be any vibrations which is going to be decreases. When I'm talking about the particular integral, there is no exponential decreasing function with the time. So we can say particular integral always be there in the mechanical system. So when you start your, you can see, you can experience that whenever a vehicle is going to be start, suddenly it vibrates with the high intensity and it goes down, but it never eliminated. It goes down, it decreases after a minimum time, after a short time, but a constant vibrations will be there after some time, after a very less time. So what is this? That when you start your vehicle suddenly there is a high vibrations you can see. So that was the complementary functions. That that was the complementary functions, but we know that complementary functions is the decreasing exponential function with time. So after a very less time, this complementary function becomes zero and particular integral remain constant. Remain constant means I'm talking about the amplitude. So this is the practical cases that I'm going to show you. So x would be equal to particular integral. This will remain in the system always. It can never be eliminated. So x would be a sine omega t minus phi. What is a representing here? A is the amplitude of the force damped system. Okay, this is the amplitude of the force damped system. This is the amplitude of the force damped system. You can see when you focus on the amplitude, this is complete amplitude here. You can see this is basically a amplitude of the force damped system. There is no time functions. This is not a time of functions. Okay, so we can say this is independent of time. This is independent of time. This is an independent of time. That means it is not a function of time. So that means with the time, it cannot be eliminated as the complementary functions decreases and becomes zero after a very short time, because complementary functions is the complementary function is the function of time. You can say, so that's why complementary functions become zero after a short time. But particular integral can never be eliminated because it don't depend on the time. That's why. So here I am going to show you the amplitude separately. Amplitude would becomes, when you compare the equations, amplitude would becomes f naught upon s upon under root of 1 minus omega by omega n to the whole square. There will be a square, okay? There will be a mistake. There will be also a square, okay? Remember one thing: 1 minus omega by omega n square to bracket to the whole square, okay? Plus 2 zeta omega by omega n to the whole square. Here you just have to correction here. Don't forget to be correct here. There will be a whole square of this bracket, okay? So this is the amplitude, basically amplitude of the force damped system. Amplitude of the force damped system. You can see there is a constant because when I draw the graph, I already show you the graph in the previous topic, but again I'm explaining you this completely because we got the particular integral value. So the graph would be like that, this and this, okay? That means this is the complementary functions. The graph would be like that. The graph would be like that. This is the vibrations. You can see after some times it becomes constant, but it is not zero. It becomes constant, but it is not zero. So like that vibrations occurs. Okay. So if I'm talking about the complementary functions, so from these conditions, complementary functions become zero. From here, complementary functions becomes zero. Only particular integral take place. There is no complementary functions. Okay. At this position, complementary functions become zero. Only particular integral will be there. This is a moment A you can consider, and this is a time, and this is a position and solution. So this is the vibration in running system. It can never stop. You can write down vibration in running system. I'm talking about running system. Vibration in running system will never stop. What is the reason? I told you that this is not the function of time, so that's why particular integral will be there. And the second point you can write down, every mechanical system must have one running life just because of this, because vibrations can never be eliminated, and vibration is not good for any mechanical system, it is harmful. So that's why, just because of this reason, because the particular integral is not going to be zero, vibration is there, so that is why every mechanical system must have one running life. You can see this is vibration. Every mechanical system every mechanical system must have one running life, must have one running life. So this is the complete force damped system. I hope you will understand this whole procedure. Now I am going to repeat again so that you will be able to understand completely. There will not be any doubt here. Okay. See here, in the vibration on the running mechanical system, also known as force damped system, we consider unbalanced forces. An unbalanced force is F naught sin omega t. Okay, and F naught maximum value we all know that. This is the equations of the force damped system. When we apply the D'Alembert principle, you will get these equations. Okay, and we know that this is what, and this everything we have studied in the previous topic. But this is new thing here in this topic, which is F naught upon n sin omega t. Okay, just because this is a running mechanical system, so it cannot be zero. The solution would be consist of complementary functions and the complementary functions and particular integral. We have seen when we study the undamped vibrations, there will be an amplitude which is the decreasing function or the exponential decreasing function with the time. So that's why it becomes zero after certain times. Okay, it becomes zero after certain times because it is a function of time. So in the very less time it becomes zero. But there will be a particular integral. So we don't know what is the value of particular integral. So we just do the process. We just have to apply the same procedure that we generally applied in the differential equations process. So when you solve the particular integral, there will be solutions that we get. P particular integral is equal to this. This is important equations. Vibrations with the frequency, force frequency or the speed omega. Okay. So after certain times, after some time, very short times, the complementary function becomes zero. So that means there will be a particular integral. When you carefully see the particular integral value, this is the function of time sine omega t minus phi. Okay, but this amplitude, I'm talking about the amplitude. Okay, so you can see the amplitude is not a function of time. So that means it will not depend on the time. That means it will never be changed with the time. Okay, so if it is not going to be changed in the time, that means the particular integral will not be zero with time. Okay, so when you start your vehicle, motorcycle, auto, whatever, Suddenly you feel there is a vibrations. Suddenly you feel when you start the vehicle, suddenly you feel highly vibrations, and after 1 second, after less than 1 second, the vibrations is minimized and it will remain constant. Okay, so the difference is when you start your vehicle you will get complementary functions because it is a function of time. There will be a complementary functions and particular integral also, but complementary functions become zero. Again, I'm explaining that when you start your vehicle, you will feel high vibrations. So this is the combination of complementary functions at the particular integral. But complementary functions become zero in a very less time. Okay, but particular integral is not going to be zero because it don't depend on the time. So that's why after certain times the vibrations is minimized, but it will remain. Okay, so that's why this is a particular integral. Here we have seen that the vibrations in the running mechanical system never stops, and every mechanical system, just because of this reason, every mechanical system must have one running light. So I hope you will understand this complete topic. We will see the magnification factor that we get from these relations. Okay. Next topic we will consider magnification factor, that is very very important. Generally, from this topic, force dynamic system, there will be a numerical questions. Generally, they ask you to find out the amplitude. They will give you the some data in order to calculate. So this is the formula that is very very important. Remember this. This formula is very important from the numerical point of view. You just have to learn this formula. Okay. So thank you.